Okay, so I'm going to repeat since I forgot to record. We're looking at your 6.1 notes, 6.1, going backwards, page 5, and we are looking at using matrices and Gauss-Jordan elimination to solve systems using row operations. Okay, so the difference between row echelon form, which is what we were doing, row echelon form is Gaussian elimination. So if you need to understand, well, what the heck are we talking about? REF, RREF? Okay, REF is row echelon form. For row echelon form, that's what we were focusing on with Gaussian elimination. We were talking about getting ones along the main diagonal, and it didn't matter what else you had in your matrix, as long as you had ones on the main diagonal and zeros below it. So maybe you had something like this, where A, B, C, D, E, and F would be constants. This was what we worked for with Gaussian elimination. And Gaussian elimination gets us row echelon form. So zeros underneath the main diagonal, ones on the main diagonal, real numbers everywhere else. Gauss-Jordan elimination is what we obtained in our calculators when we use the RREF operation. So for Gauss-Jordan, what we end up with is starting out to be similar to what you had with Gaussian elimination. The difference is that anywhere that's not the main diagonal, you're only going to have zeros. And then you'll have constants to the right. That's reduced row echelon form. Now, when we did this in our calculators, we did the RREF function, and what we ended up getting was something that looked like Gauss-Jordan form. So ones on the main diagonal, zeros everywhere else. Now, the nice thing about Gauss-Jordan form is that if you can get your matrix into Gauss-Jordan form, you don't have to go back and back substitute, because you don't have to worry about, well, now I've got y plus cz equals e. Doesn't matter, because you don't have cz anymore. You just have z equals c, y equals b, x equals a. And you don't have to do the back substitution. So no back substituting. That's the big difference here. Now, what we focused on doing by hand last week was taking matrices and writing them into REF form, row echelon form. What we're going to work on today, only for 2x2 matrices, is Gauss-Jordan form. And I don't want to spend a whole lot more time on row operations today, because we do need to get into 6.3, but I did want to show you this. And I'm going to put a little bit of a note here. You will be required to solve 2x2 systems by hand using Gauss-Jordan form. So I'm going to have one question on the quiz where I'm going to give you a system of equations with 2 equations and 2 unknowns. And I'm going to ask you to use Gauss-Jordan elimination to solve the system. And when I ask you to do that, what I'm looking for you to do is get your matrix into something like this. And really, it won't even be that complicated, because you'll be looking at a 2x2 matrix. So what you're going to be looking at for a 2x2 looks like that. You're going to want ones on your main diagonal, zeros everywhere else, constants on the right. And that's essentially what this information here is telling you. Now, some years, depending on how much time I have, we go through actually working on putting matrices that are 3x3 in this form. Other years, I only do 2x2. This year will be a 2x2 year. All right, so the directions are: get ones in the upper left, use the one in the first column to get the zeros below it, so on and so forth. And a lot of this should be familiar to you. The difference is that now you're working your way sort of in the opposite direction to try to get a 0 here in the upper right. So let's go ahead and do this on an exercise, which is on the next page. I have a system of equations on page 6, and it's got 2 equations, 2 unknowns. Before I do that, does anybody have a question about REF, RREF, and what you're going to be required to do? Okay, so on your exam, if I tell you solve a system of equations using matrices, you're going to be using Gaussian elimination, which is what we did in 6.1 throughout this whole thing. So you're going to be getting it into this form and back substituting. Now, if you really feel like you want to get it into Gauss-Jordan form, that's fine. Show me the work and get it there instead of back substituting. I think back substituting is easier than doing this, but I can't stop you if you like that. But anyway, so on a task, you will have to solve systems like this, 3 equations, 3 unknowns, but only using Gaussian elimination. For Gauss-Jordan, you're going to be asked to do something like what we have for number 8. Okay. So we're going to take this system of equations for number 8, and we're going to first of all write it as an augmented matrix, and then we're going to focus on getting the 1s in the main diagonal and 0s everywhere else. And it's a slightly different way of thinking in order to get this 3 to become a 0, or whatever it will be in just a moment. So go ahead and write this into an augmented matrix. And anytime you're rewriting something, double check it a couple times. Make sure that all your signs are correct. Okay. So you would like to have 1s along the main diagonal. I would focus first on probably getting this 6 to be a 0. Same way that you were doing this before. To start out, oh, you know why? This is, there you go. Okay. So we're going to take the 6 first and make it a 0. You have a couple of different ways of doing this. To make it easiest, I would probably say we're going to take our new row 2 as being, oh, let's see, 6 and 4. I can make them both 12s. You can go with 24 if you want, but I could also make one of them a 12 and one of them a negative 12. So maybe I'll do that. So I'll take negative 3 row 1 plus 2 row 2. Let me try to make sure my notation is consistent here. So negative 3 row 1 will make this element a negative 12, and then a 2 row 2 will make this element a positive 12. But there's more than one way of doing that. That's just the way that I would suggest. Okay, so negative 3 row 1 is negative 12, negative 9, negative 3. And then 2 row 2 is positive 12, negative 2, negative 30. Double check all your signs and make sure everything looks good before you add. Add them up. You should also be noticing that when you add these and you get 0, negative 11, negative 33, you have a common factor of negative 11. So if I were you, make your life a little bit easier and reduce these coefficients down to smaller values. I'm going to divide by negative 11. So I'll get 0, 1, 3. Okay. Now we're going to put that back into the matrix. The first row has not changed. That is still going to be 4, 3, 1. go back to your original first row. The new second row will be 0, 1, 3. I went backwards here. Do we have questions so far? Okay. Now this is a point where you might be like, okay, why can't I just back substitute? Because now I already know that y is 3, and I know that 4x plus 3y is 1. Yeah, technically, but we're doing an exercise right now, which is how to get this matrix into reduced row echelon form. So that's what we're going to do. In order to do that, I need to focus now on, yeah, I do need ones on the main diagonal. It's not a big deal to divide by 4 at the end. What I really want to do is get this one to become a 0, because then what I want is I want to have zeros everywhere else. Now, if I want to make this guy a 0, then I can take row 2 and multiply it by -3. And that'll be our new row 1. Okay, so this is what I would be expecting you to do on an exam when you're doing this by hand using reduced row echelon form. Okay, so -3 row 2 plus row 1. Will look like this. So row 1, I said that backwards, plus -3 row 2. And then add them up. You should get 4, 0, -8. And here's another case where life works out so nicely for you. You have a common factor of 4 divided out. You'll get 1, 0, -2. Okay. So we are going to replace our row 1 with this nice new row 1, which is 1, 0, -2. And row 2 stays the same. Now you have a matrix that is in reduced row echelon form. Which is excellent. And now you don't have to worry about back substituting, because you know that y is 3 and x is -2. So when you write your solution set, x is -2, y is 3, and you're done. You can go back and check your solution if you should so desire. Okay, questions on this one? Okay, because I'm not going to do another one of these. I feel like they're pretty straightforward. It's just basically a slight variation on what we did before, a little bit easier because you have fewer rows that you're dealing with. Okay, now one other thing we didn't talk about last time was taking a 4x4 system and just finding the solution. I just want to remind you of how to do this in your calculator. So for number 9, you have a system of 4 equations and 4 unknowns. Write the augmented matrix, write the reduced row echelon form of the matrix, and write the solution. This is something that you can easily just do in your calculator. If I have you do something like this on the test, I'm going to ask you to write these things out. I don't just want you to give me a solution. I want you to at least write down the matrices. Once you put it in your calculator, fine. I'm not too worried about that. I just want to make sure that you know what you're entering in your calculator and that I can see that you know what you're doing. So your augmented matrix, you're going to use your coefficients, starting with the first row. 3, 5, 0, 2. And it might seem odd, but usually whenever you are given a system with 4 equations and 4 unknowns, the W comes after the Z. Not always. Sometimes you'll see it as W, X, Y, Z. It can be either way. Just make sure that you maintain continuity here. 2, 0, 6, -1, -5. Zero, -2, 3, -3, -3. -1, 2, 4, 1, -2. Now, back in the day, this would have probably been like an extra credit, do this by hand question, just because I don't usually force people to do that. But, you know, times are a-changin'. All right, so that's your augmented matrix. Now, let me remind you, in case you forgot, how to enter this in your calculator. My handy dandy emulator. I'm going to verify that it is showing here. There it is. Okay. Remember, when you're entering your matrix, you're going to go to second matrix. If you want to use A, fine. If you want to do something different and use B, fine. Oh gosh, I forgot edit and then go down to B. I always do that, like every time. Okay, edit, and then I've selected B. Enter. Now it's going to give me a blank matrix. Remember that what you're looking at is, for a matrix, the dimensions are R times C, rows times columns, or RC COLA, which for some reason is the way I've always remembered matrix dimensions. Okay, so the number of rows that we're looking at is 1, 2, 3, 4. And the number of columns, even though I know technically you have 4 columns on the left, well, we're looking at 5 columns because we need to include that right-hand side for your augmented matrix. So I'll go with 5. Enter. Now go through and enter all of your coefficients. So we have 3, 5, 0, 2, -12, so on and so forth. If you see me enter anything wrong, tell me. All right, now I'm going to double check. Ben's calculator has given him an undefined error. When did it give you the error? Like it won't let you enter the matrix? Or when you were trying to do the RREF? Won't let you enter the matrix. Undefined error. It doesn't say like dimension error or something? Does it always do that or just now? Just now. Interesting. My suggestion is go back to your matrix menu and maybe try to enter a different one. I don't know, something weird. I don't know what might have possibly happened. Or maybe go back into matrix A and edit it and change it into a 4x5. I don't know. Like you fixed it? Yeah, okay, wonderful. Anybody else having calculator issues that I can not know how to fix? Sometimes I really do. Okay, wonderful. Okay, go back to your home screen. Go back to your matrix menu. You are going to go to math. So scroll to the right and then scroll up for RREF. Enter. And then I used matrix B, so I'm going to go back and pick up matrix B. And then enter. And there's the reduced row echelon form, which you could have spent 15 minutes working on, and there it is right there in your calculator. So you should have ones on the main diagonal, zeros everywhere else, and on the right-hand side, -1, -3, 0, 3. So the last part that I did, Sebastian, was I went into, I went to the home screen first. If you forget to go to the home screen first, I don't know, weird things happen for me anyway. Go to second matrix, scroll to the right for math. And then to get to RREF, I scroll up because it's faster. And then I hit enter. And then I need to enter a matrix. So I go back to the matrix menu. I scroll down to matrix B or hit number 2 and hit enter and then enter again. Got it? Okay, wonderful. Anyone else questions about how to find this reduced row echelon form matrix in your calculator? Okay, wonderful. So your solution for your first variable, which in this case is x, you have -1 and then -3, 0, 3. So write them from left to right, the order in which they appear in RREF, which is from top to bottom. So the top to bottom will turn into left to right. Oh, sorry, now I'm still sharing this calculator. Oh, let's see. If we don't have any calculator questions, I'll dump that. Go back here. Okay. So I've written the RREF form from my calculator and then the solution down here on the bottom. Any questions about how to work on this 4-variable system of equations on your calculator? Okay. Now remember that I'm going to be asking you to do this on your test by hand. Technically, you can do this in your calculator, you'll get the same answer, but I want to see your row operations. If your row operations don't turn out to give me the answer that you got, you're not going to get the points because I'm going to know that you've got your calculator that you're relying on, and I'm going to know that something doesn't add up. You have to show me your work, and you have to show me that your work leads to the conclusion that you got. Okay. The last thing I wanted to do in 6.1 was I thought it would be a good idea for us to go through this word problem because we haven't done a word problem with 3 equations and 3 unknowns. So number 10 and 6.1 I think would be a good idea. Ron attends a cocktail party with his graphing calculator in his pocket. Of course, hello. Doesn't everybody? He wants to limit his food intake to 133 grams of protein, which is a lot for a cocktail party, I have to say. You know, it takes a lot to get to 133 grams of protein. 120 grams of fat, also a lot, and 165 grams of carbs. So according to the health conscious hostess who knows everything about her food, or his food, the marinated mushroom caps have 3 grams of protein, 5 grams of fat, and 9 grams of carbs. The spicy meatballs have 14 grams of protein, 7 grams of fat, and 15 grams of carbs. And the deviled eggs have 13 grams of protein, 15 grams of fat, and 6 grams of carbs. How many of each snack can he eat to obtain his goal? So remember that when you're assigning your variables here for these application problems for systems, you're looking to the question. The question is, how many of each snack can he eat to attain his goal or obtain his goal? You know that you have 3 different kinds of snacks that are available. You have marinated mushroom caps, spicy meatballs, and deviled eggs. Those are the kinds of snacks that you have available. So let X be the mushroom caps. or the number of mushroom caps he can eat, whatever. You can let y be the spicy meatballs. And then z could be the deviled eggs, or the number of deviled eggs. Okay. So X, Y, and Z will be the different snacks that he has at his disposal. Your equations, however, are going to be set up to rely upon his limits here. So for instance, you know that he wants to limit his food intake to 133 grams of protein and 120 grams of fat and 165 grams of carbs. You know the amount that's in each one. Like for instance, I know that each mushroom cap has 3 grams of protein. So that means I'm looking at X mushroom caps times 3 grams of protein plus Y spicy meatballs and the protein that's in that, et cetera, et cetera. We want that to be equal to 133. And I know you might be thinking, well, he's limiting it to 133. So isn't this technically like an inequality system? I guess, but imagine that he's going to be eating 133 grams of protein, 120 grams of fat, and 165 grams of carbs. That is what he's going to eat. We're not going to make it less than or equal to in this case. All right, so the first equation we're going to write is going to be a protein equation. So let's see. Mushroom caps have 3 grams of protein. So 3 grams of protein per mushroom cap. Let's see. The spicy meatballs have 14 grams of protein. So 14 grams of protein per spicy meatball. And the deviled eggs have 13 grams of protein. And so on and so forth. So you're going to write 3 equations like this. The next one is going to have to do with fat. So let's see. As far as fat, we have 5 grams in the mushroom caps. The meatballs have 7, and the deviled eggs have 15. And he's trying to limit this to 120 grams of fat. And then you're also going to talk about carbs. So as far as your carbs are concerned, you want to be at 165. We're looking at 9 for the mushroom caps, 15 for the meatballs, and 6 for the eggs. Now, I'm not going to have you solve this by hand, but we can write an augmented matrix. And we'll solve it in our calculators. Does anyone have a question on the setup or the augmented matrix? Okay. I also feel like I should mention when we're working on these on the tests, I will have a couple application problems for you on here. I will specify whether or not I want you to do this by hand or use your calculator. Most likely, I'm going to have other exercises ready for you to do by hand. If I'm doing a 3-variable system that has large numbers in it, like this one does, I'll probably ask you to do it in your calculator, but you should technically know how to do these using Gaussian elimination anyway. But I will specify on the exam. So go ahead and enter this into your calculator. And I am going to go back and edit my matrix A. Sometimes I have matrices in here that are of specific dimensions, and I just edit the ones that have the dimensions that match the ones that I need. I don't know, just something that I do. So I know I need a 3 by 4, and I'm going to go ahead and enter these coefficients. Mm-hmm. And make sure you're writing down everything you enter, because let's say you accidentally, get the wrong key in your calculator and you enter a 5 instead of a 15, and then your answer is wrong. Well, I can't give you any credit then because I have no idea what you even entered. Whereas if you gave me your original matrix to start and ended up getting a different answer, well, at least I'll know you just entered it incorrectly, but it wasn't that you had no idea how to set it up. The setup is important here. So there is your augmented matrix. Going back to my home screen, I'm going to go to the math menu, scroll up to RREF, and I'm going to select matrix A. And we get x equals 8, y equals 5, and z equals 3. So that makes 8 mushroom caps, 5 spicy meatballs, and 3 deviled eggs. Before I move the calculator away, does anybody have a question about how to solve this using your calculator? Okay. Okay, so that was just another application of systems of equations. Before I get into 6.3, there's one more thing I want to do here. And that is in 6.2. I wanted to give you an example of a situation where you have more equations or more variables than equations. So in 6.2, when I went through the notes, I went over this situation where you have no solution. So I just want to remind you what no solution looks like. You go through the row operations, you get all the way down to the bottom, and you get zeros on the left-hand side of the bottom row. And then you'll get something that's non-zero to the right of that bottom row. This is a situation where you have no solution, because remember, that means that 0z equals 6. Well, 0 can't be equal to 6. So that is a no solution situation. All right, I'm not going to go over this one, but if you want to work on it in the office hour, technically I accidentally sent you the key instead of the actual blank notes anyway, so you should have it written down. But otherwise, same idea. It's a no solution. But if you're unsure of the work or you wanted me to check something, stick around for the office hour and I'll go over it with you. And same goes for number 2. Because what I did for the second page here in your 6.2 notes is I went over this scenario where you end up having infinitely many solutions. And remember, when you have infinitely many solutions, you get to this bottom row and you end up with all zeros. So remember, no solution was zeros on the left and then a constant. Well, if you have infinitely many solutions, you have all zeros on that bottom row. So this was what that quiz question was asking you about on your quiz today. If you have infinitely many solutions, you're going to write your solution set in terms of your variable z. So you're assigning z, and then you're back substituting. So y minus 5z equals 4, y equals 5z plus 4. That goes in your solution. And then back substitute for x the same way. X minus 2y minus z equals 5. Well, substitute in x. Substitute in z and then substitute in y written in terms of z. And then you'll get an expression for x in terms of z. And your solution set at that point will look like this. So again, number 2 does the same thing. If you have questions about it, stick around. You should have the key to it anyway, but if you have questions, please let me know. So the last thing I wanted to talk about in 6.2 was a situation where you had a system with fewer equations than variables. And you'll find that this looks similar also to all of the other row operation problems that we worked on. I just want to show you how it could look slightly different. Now, you know that in this case, you're not actually going to get a solution. It can't be. In order to get a solution to a system of equations, you have to have at least as many equations as you have variables. So in a situation like this, you're going to end up having to write your equation in that infinitely many solutions form. Or it's possible that you could have no solution. But go ahead and write this as an augmented matrix: 5, -1, 1, 8, and 7, 1, 1, 6. Now, you're going to do the best you can with getting this into row echelon form. You don't have that same square matrix over here on the left, but that's fine. Your goal is still going to be to make this bottom row left corner a 0. In order to do that, I would make both of these coefficients 35. So one of them will be 35, the other will be -35. So we'll just have them be additive inverses of 35. So I'm going to do -7 R1 plus 5 R2, and that'll get us to our new R2. Any questions on why I'm going this route? Okay. So -7 R1. Be careful with your signs here. Make sure that they're the opposite of what they were before. And then 5 R2. And add them up. If you see that there's a common factor, you might want to just go ahead and divide it out. I mean, like for instance, I'm going to divide by 2 just because I would like to have some smaller coefficients to deal with. And then we'll put this back together. So our first row is unchanged. The second row will look like this. Now, I did not actually give you the explicit instruction to write this in row echelon form. Oh, Sebastian, what are you saying no to? Was it to whether or not you had questions? Sorry, I just noticed your no. Oh, okay. Just making sure. I didn't know if you were just objecting to the lesson as a whole. Okay. Excellent. Wonderful. Okay. So I didn't actually say get this in row echelon form. So whether or not you decide to make these values 1s is up to you. Technically, your main diagonal is this one. In this case, because these values are not factors of all of the other values in the row, I would say just let it be. But you're going to have to get a solution here. In a case like this, you have a value z. You're not going to get a solution when you have fewer equations than you have variables. But you can have a situation where you either have no solution or infinitely many solutions. This clearly is going to have infinitely many. So let's go through and work our way backwards. We're going to let z, again, just be z. And we're going to write everything else in terms of z. So we have 6y minus z equals -13. And then you're going to go back and solve for that in terms of z. So you want to have y equals blah, 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 z. So add z to both sides and then divide by 6. When you do that, you'll get 1/6 z minus 13/6. And then you'll do the same for x. I'm going to just put a box around this because I'm going to use it in my final solution. But I'm just holding on to it for right now so I don't lose track of where it went. Okay, let's see. Now I have 5x minus y plus z equals 8. 5x, and I'm just going to move everything over to the other side, equals 8 plus y minus z. Gosh, we're totally running out of room here. This is terrible. 5x equals 8 plus, and then y is 16z minus 13/6, and then minus z. Now remember, this is 5x, not x. 8 minus 13/6 is 35/6. And then 16z minus z is 16 minus 66 is negative 5/6. And then divide each term by 5. So negative 5/6 divided by 5 is negative 1/6. And then 35/6 divided by 5 is 7/6. Negative 160 plus 7/6. Sorry, clearly we needed more space there. And these are all going to be dependent on one another. So when you write your solution, this will be the ordered triple. X, Y, Z. Looks like that. Are there any questions on that one?
Will there be a question like this on our test?
There could be. Yeah. I don't know. I'm so far away from writing your test. I have no idea when that's going to happen. So I cannot say for sure, but it's definitely possible. There'll definitely be one where you have to write an answer like this, but whether or not it will be a system with 3 variables and 2 equations or 3 variables and 3 equations, I could not say. Any other questions here? Wonderful. Then let's talk about matrix operations in 6.3. Oh, and don't worry about this application. I always find it to be a weird application. There is one similar to this in your book, but I'm not going to assign it. You will not be responsible for that. I find it confusing. Okay. Oh. All right, so 6.3, I kind of feel like after all these row operations, getting into 6.3 is kind of nice. You take a deep breath and you realize, oh, I have a little bit of an easier section coming up here for 6.3. So that's kind of nice. Usually you see the easier section at the beginning and not section 3, but that's okay. Okay. We need to talk about matrix operations because we need to learn to multiply matrices for section 6.4. We're going to be doing all kinds of things with matrices. A lot of them are super straightforward. I know it's kind of weird too that you've been using matrices now in 2 sections, and then all of a sudden in 6.3 they're like, oh, hey, by the way, this is what a matrix is. I'm like, okay, you could have told me that at the beginning. So it's kind of just the weird way that your author structures this particular chapter. Okay, so a matrix is an array of numbers arranged in rows and columns placed in brackets. We can represent a matrix in two different ways. Okay. I think my two got cut off. A capital letter, such as A, B, or C, can denote a matrix. We're going to be using that a lot. This is pretty much always the way that you're going to see it. A lowercase letter enclosed in brackets can also denote a matrix. You might see that here and there, mostly just in this particular section. A general element in matrix A is denoted A sub ij. I know that that print is super small, but you should be able to read that on yours, even though you can't see it as well on my screen. So it's A sub ij, and this refers to the element in the ith row and jth column. So when you're thinking about rows and columns, I would be representative of the rows and J would represent the column in which that element presides. A matrix of order m by n has m rows and n columns. Now, remember that I kind of talked about this by using my mnemonic RC, rows times columns. So m would be the number of rows and n would be the number of columns. So what we're going to talk about is just, first of all, just little definition stuff having to do with matrices. Give the order of the matrix and identify the given element of the matrix. So the order is just the number of rows times the number of columns. So the rows, remember, are horizontal. So we have 2 rows. And then the columns are up and down, vertical. So we have 4 columns. I know it's sometimes easy to switch those around. You got to remember the proper order for those. And then you're being asked for the element A sub 1, 2. I know this looks like A sub 12. You're looking at the 1th row, which is the ith row or the first row, and the 2nd column. So the 1 represents the row, the 2 represents the column. So when you're looking at the first row, 2nd column, you come up with this element of 8. Does anyone have a question about number 1? Understand what is meant by equal matrices. You will find this to be fun and refreshing. If m equals n, a matrix has the same number of rows as columns and is called a square matrix. So if the number of rows equals the number of columns, then you have a square matrix. So a 3 by 3, a 4 by 4, a 2 by 2, etc. 2 matrices A and B are equal if and only if they have the same order and you have the same elements in the matrices. So we are going to do now some equating of matrices. In order to solve these matrix equations, if you want to say that, you have to have the same order on the left as on the right. If you don't have the same order, then you can't solve the matrix. But you'll notice that on the left, you have a 2 by 2 matrix, and on the right, you have a 2 by 2 matrix. So in order to solve for the missing variables here, you're just going to take the element from the left and set it equal to the element in the right. That's it. This is really not supposed to be some crazy challenging thing. So you know that x has to be 1 because x is in the first row, first column, and 1 is in the first row, first column. Y has to be 7 because they're both in the first row, second column. Now, 9 and 9 are already the same. You don't have anything to do there. And then z is equal to -8. So you just found the values of the variables and you're done with that one. A whole lot easier than row operations, huh? Lot less work, I should say. Questions on number 2? I didn't think so. All right, so now we're going to add and subtract matrices. Now, in order to add and subtract, again, you're in a situation where the matrices have to have the same order. So if A, B, and C, and remember a lot of times we denote matrices by using a capital letter. So A, B, and C in this case are all matrices. If they're n by n matrices and 0 is the n by n 0 matrix, then the following properties are true. Addition, the commutative property for addition holds. So A plus B and B plus A, same matrix, no big deal. You're going to find that that's not true when we talk about multiplication. So matrices don't necessarily have the same rules as adding whole numbers or adding real numbers. You can group the addition in either order and you will still get the same sum. So the associative property holds whether you decide to add the first two first and then add the third one, or whether you decide to add the second two matrices and then add in the first one. Doesn't matter, you decide. The 0 matrix can be added to any matrix, any non-zero matrix A in either order and you'll still get A. 0 plus A is A. 0 plus a number is a number. 0 plus a matrix or a matrix plus 0 still gives you that same matrix. And then the additive inverse property still holds. A plus negative A or negative A plus A will still equal 0. So that's good. You still have those definitions that are true and I feel are pretty, you're pretty used to seeing them at this point. Okay, so here is an example of matrix addition. No big deal. You're going to add each element and each corresponding row and column. So you're looking at the elements in each piece of the matrix and those you're just going to add together. So the first row element and the first row, first column element gets added to the first row, first column element, so on and so forth. Same with subtraction. Just be a little bit more careful with subtraction because you could be doing minus a negative. You know how to subtract numbers. But I don't expect anyone to have a problem with this. So let's do number 3. We're going to let A be this matrix and B will be this matrix. Find A minus B. If you would like, and I always have students who just skip right to the answer here. That's fine. I mean, you don't have to write out all the work here because it's pretty much, you're just looking at -1 minus 7. I mean, literally, it's just doing that. So if you don't want to write that out, that's fine. But since I'm the teacher, I'm going to write it out. Okay, so your first element here will be -1 minus 7 in the first row, first column. Moving to the first row, second column, then you'll subtract those elements for A minus B. So you'll take 4 minus 2. And what I'm doing here is I'm creating a matrix that represents the difference, and it's also going to be a 3 by 2. And I'm going to write their orders here just so you get used to seeing them. Remember that in order to add and subtract matrices, they have to have the same order. Moving on to the second row, first column, we have 0 minus 17. Second column, 4 minus 4. And in the third row, first column, 9 minus 4. Second column, -4 minus 2. And then you're just going to simplify. And that's your answer. Are there any questions about subtracting these matrices in number 3? Okay. Now we'll find A plus B. Do the same thing. I feel like most of you are already working on this on your own, which is fine. And of course, like all of the elements in that right matrix are negative. All right, that's what I got. 0, negative 16, negative 11, 0, and 2, negative 15. Now, like I said, on a test, this is something that's basic enough that if you did not include this step, I'm okay with that, because really there's not a whole lot to show here. If you can do this, then you can do that, and it's not that huge of a leap. So don't feel like you have to write everything, but if you want to write more, and like, let's say this was wrong, well, you'll get more points if you write your intermediate work, because then I can say, oh, well, they knew that they had negative 8 plus negative 3, but you know, maybe you called this negative 5 instead of 11, negative 11. Maybe you added 3 instead of adding negative 3, something like that. Where that's probably a case where I would probably just like cross it out and not even take off points because it's something so little. But if you just wrote the answer and got it wrong, that's a little bit of a different story. So that's why I always encourage people to show extra work, even if it's not necessarily needed. Okay. Now we have 2 different ways that we multiply matrices. The first way that we're going to use multiplication with matrices is scalar multiplication. Now we can multiply a matrix by a scalar, and that's not the same as multiplying it by another matrix. A scalar is just a number. A matrix, you know, is an array of numbers. So we're going to let A be a matrix of order m by n, and C is a scalar. So C times A is this m by n matrix just given by CA equals C times each element in the matrix. So what you're going to do for the scalar multiplication is you're just going to multiply each element of A by the real number C. So no big deal there. Properties for scalar multiplication. Well, you can multiply CD times A or C times DA. You have that associative property that holds for scalar multiplication. You can multiply 1 by matrix A and you'll still get A back. You have the distributive property that works, and this works for scalar multiplication. And then you also have a distributive property that holds whenever you're multiplying by a sum of scalars. So number 5 is asking for 2A. When you are trying to find 2A, you're going to take 2 and multiply it by each element in your matrix. So you're just taking each element and multiplying it by that scalar. So that just looks like negative 6, 6, 0, 4. Now, matrix multiplication, when we get to it on the next page, is going to be more work. But scalar multiplication, you're just multiplying that number through the matrix. Does anyone have a question so far? Okay, I feel like I'm covering these a little fast, but that's because I don't want to spend a whole bunch of time doing something that's super straightforward. I'd rather spend that time doing, spending more time on matrix multiplication or min application maybe. Okay, next we're going to take 4A plus B. So now we're going to combine scalar multiplication and matrix addition. So I need 4A. Now I'm going to do 4A first. And this is where I would recommend you actually including more work, because you have 2 different steps here. Try not to skip out, or if you're doing a lot of mental math, something might go wrong. First, I'm going to take 4A. That means I'm taking 4 times 3325, which is 12, 12, 8, 20. So there's your 4A. And now I'm going to add that to B. Now, if you want to rewrite this, just showing the addition in each element, that's fine. But if you feel comfortable with the addition and just saying 12 plus 0 is 12, do that. 12 plus 4 is 16. 8 plus negative 1 is 7. And 20 plus 6 is 26. Questions on number 6? Okay. Wonderful. Now we're going to solve a matrix equation for x. Now what I suggest you do, and maybe you don't have to do this in every single one. This one's a little bit more straightforward, but I would take the equation that you're given and solve that for x first so that you know what to do with the matrices. So if I'm looking for x in this situation, what I'm really looking for is, if I'm looking for x plus a equals b, I'm looking for x equals b minus a. Now, if you wrote that differently, you might have written x equals negative a plus b. You should still come up with the same matrix because really this is just plus a negative anyway. So I'm going to take b minus a. So I'm going to take the elements in B and subtract off the elements in A. So 3 minus 4, negative 4 minus 2, 4 minus 3, and negative 5 minus 5. And you'll simplify that to negative 1, negative 6, 1, negative 10. Questions on 7? Okay. Number 8 is another equation. For number 8, you have a coefficient on x, which is fine. I still think that it would be best for you to solve for x before you do anything with your matrices. So looking at your equation, simplify this out to solve for x. You'll have 4x equals b minus a, and you don't actually want 4x, you want x. So divide both sides by 4. If you would like, instead of dividing by 4, you can multiply by 1/4, whichever seems most reasonable for you to do. Scalar multiplication really is also going to be scalar division in this case. So you can either multiply the matrix by 1/4 or you can divide each element by 4. It's doing the same thing. So first I'm going to take b minus a. Make sure you're using your parentheses here, or if you're looking at it this way, you don't need to worry about that. And then we're going to divide it by 4. So x equals, we said b minus a over 4. So that means, or if you're thinking about it as 1/4, that's fine too. B minus a, so 11 minus 6. 0 minus negative 6. Be careful there with the double negative. 0 minus negative 8. Negative 2 minus 0. 6 minus 11. 7 minus 7. Questions before I proceed? So simplify your matrix and then perform your scalar multiplication. And now multiply through by 1/4. You'll get 5/4. 6/4 is 3/2. 8/4 is 2. Negative 2/4 is negative 1/2. And you'll have negative 5/4. 0 times 1/4 is still 0. So I'm going to be putting some of these on the test for you. They should be easy points. These should not be things that are missed. Historically, they are not missed. Usually students do just fine on these. You guys do number 9. Solve the equation first. If I were you, I'd probably add x to both sides and then subtract 3a. But you do whatever you want to do. When you solve for x, you should be looking for b minus 3a. And I would suggest you find 3a first. You should have -3, -21, -3, 2, and -21, 33. Any questions on number 9? Number 9? Okay. Then let's talk about how to multiply matrices. So of all the things you're going to do in 6-3, this is the trickiest, but it's certainly not as tricky as row operations. Certainly not as involved. Okay, now there's a definition here, and this assumes that you're multiplying 2 by 2 matrices. Now, when I show students matrix multiplication, I don't even give definitions. I just say, watch me do this, and I do it a couple of times until you feel like you get the hang of it. What you're going to do is you're going to multiply 2 matrices by taking the first row of the first matrix and multiplying it by the first column of the second matrix and adding up the products that you're getting. So notice how you get AE plus BG. The reason that you're getting that is because as you go along the first row, first column, you're going to multiply. So you're taking A times E plus B times G, and you sort of do it visually across and down. So the first row, first column will be the first row, first column elements. And when you're looking for the first row, second column, you're going to look in the first row, second column. So doing the same thing this time using AB and FH. So that'll be A times F plus B times H. So we're kind of going across and down at the same time, if you can see this visual occurring. Now, notice that when you go to the second row, first column, you're using the second row, first column. So same idea, C times E plus D times G. Second row, second column, C times F plus B times H. So as you're moving from left to right, you're going from top to bottom. And you're always using whatever row and column you're trying to find. That's a 2x2. You're going to have to do this with bigger matrices. And you're going to have to figure out when you can and can't multiply matrices. Now, we know that we can add and subtract matrices as long as they have the same order. That's not necessarily the case with multiplying matrices together. The product of an n or an m by n matrix A and an n by p matrix B is an m by p matrix. So if you're thinking about what that means, you're taking matrix A, which is m by n, and you're multiplying it by matrix B, which is n by p. In order to multiply two matrices together, it must be the case that these two inner numbers match. So these two inner values, whatever they are, must match. That's very important. So before you multiply the matrices, you might want to go ahead and write out their orders so that you can verify that these inside values match. Now, you have to multiply them in this order. Notice, by the way, that if we tried to multiply B times A, you would have n by p and m by n. In that case, you can't multiply, you cannot multiply B times A because the inner dimensions don't match. So you cannot multiply B times A in this case. So it's really important that we write out the order of the matrices. We verify that these inside dimensions match. When they do, the product of the matrix that you're multiplying, or the product of the matrices that you're multiplying, is going to be m by p. Those are your product dimensions. So when you multiply these two matrices together, the dimensions of the product will be m by p. The two inner values must match in order to be able to multiply them. So that's really, really crucially important. If you find this whole slew of information helpful, be my guest, use it. I'm just going to keep just doing a visual as we go down the rows and columns here. Find the product AB, if possible. For the product of two matrices to be defined, the number of columns of the first matrix must equal the number of rows of the second. So go ahead and write out the dimensions here. So you have 2 rows, 2 columns in A. And for B, you have 2 rows, 3 columns. Notice that your inner dimensions are both 2. So that means that you can multiply. Check. Now the product that you're looking for is actually going to be a 2 by 3. Sometimes when I do this, I actually write out a 2 by 3 matrix so that you have an idea of what you have left to find in case you derail somewhere. So 2 rows, 3 columns. Now, you're going to need some extra space because you're going to be writing this times that plus this times that. But 2 rows, 3 columns will look like this. So we're going to go through and fill this out, and then we're going to simplify. Any questions before I do that? Okay, so I'm looking for, first of all, the element in the first row, first column. So I'm going to start out with the first row and the first column. So -1 times 0, and you're always adding here, plus 3 times 1. So I went just across and down. I'm going to do the same thing for the first row, second column. I'm going to use the first row, second column this time. So -1 times -2, 3 times -3. And once you get the hang of this, you won't have to put as much thought into it. For the first row, third column, you're doing first row, third column. -1 times 5 plus 3 times 2. Questions so far? Okay. Okay. Now we're moving on to the second row. So forget about your first row of A, move on to the second row of A. And we're going to go through all 3 columns of B now. Second row, first column will be second row, first column. 1 times 0 plus 4 times 1. Did I say 1 plus 0? I meant 1 times 0. I'm not sure. It's looping back in my head funny. 1 times 0 plus 4 times 1. Second row, second column. Second row, second column. 1 times -2 plus 4 times -3. And second row, third column uses the second row, third column. 1 times 5 plus 4 times 2. Now, if you've done this correctly and you maintained an ordering here, you'll see that you have 0s, 1s, -2s, -3s, 5s, 2s, and then 1, 3, I'm sorry, -1, 3, -1, 3, -1, 3. 1, 4, 1, 4, 1, 4. So if you maintain order, you're going to see that you have this pattern that's repeating, and you'll know that you did this correctly. Now all you have to do is simplify by just simplifying these expressions in each blank. So 0 plus 3 is 3. 0 plus 4 is 4. Then you have +2 minus 9. -2 minus 12. -5 plus 6. And 5 plus 8. And there's your product. Questions on number 10? Now, I started out just by writing these blanks. You don't have to do that. I just think sometimes it's helpful if you know what to expect. If you kind of go into it blindly, sometimes you get confused. Number 11, write down your dimensions. So 2 rows, 3 columns, 2 rows, 2 columns. Can I multiply these matrices? No, because my inner dimensions don't match. So you cannot multiply these matrices. You're going to see some of these for your MyMathLab homework. If you just get started and you don't think about it, you're going to get so confused, and you're going to find a way to multiply them, and you're going to say, wait, but this looks right. I got an answer. just be careful. You can't multiply these. Don't try to find a way to do it. It's not going to happen. So there are going to be two options. One will be the product A times B is, and then you're going to enter your matrix. There's going to be a template for you. Pick the matrix, enter your elements. The other option will be you cannot multiply these matrices. Questions on 11? Number 12. All right, so we have our rows times columns, 1 row, 3 columns. I know this is going to look so weird because you're thinking, wait, there's no way we can multiply these together. This doesn't look right. But actually, you can multiply these together because their inner dimensions are the same. Check. Just make sure that you're doing rows times columns, because if you do columns times rows, then you're going to get the wrong conclusion. Your result, A times B, is going to have the dimension 1 by 3. So you know that you're looking for, in the end, a matrix with 1 row, 3 columns. Hopefully I left us enough space there. But if history has taught us anything, I probably haven't. So maybe I should leave us a little more space down here. The reason I think we might need a lot of space, by the way, is because there are a lot of numbers in that second matrix, and they're all going to have to come into play somewhere. So you're going to need a lot of space here before you simplify. Include more space. Okay. So my matrix will be 1 row, 3 columns. I'm going to take the first row, first column will be the first row, first column. So 6 times 9 plus -1 times 6 plus -1 times -1. So I just took all the elements from that first row, or the only row in this case, and multiplied them by all the elements in the first column of B. And then I'm adding them together. And we'll simplify in a second. And this is definitely something where I'm expecting you to show your work. This is not like a just give me the answer thing. You have to show me your work here. Okay, first row, second column. So I did the first row by the second column, and I added up all the little products. Now for the first row, last column. We have this. And again, you have 6, -1, -1, 6, -1, -1, 6, -1, -1. And then you're going through and noticing 9, 6, -1. Good. -4, -9, 5. Good. 6, -4, -9. Wonderful. Simplify. If you need your calculator, that's fine. Use your calculator. I mean, you don't want to worry about making mistakes. So if you need to use your calculator, I'd rather have you do that than just having little tiny things that go wrong. All right, I got 49 -20 and 49. All right, I only have 2 minutes left. So the applications here are, I mean, they're not the best. I'm going to give you the answers though. So in case you want to work through them, that you can do so. And a lot of these, like for numbers 13 and 14, I didn't even have any work because there was really nothing to do there. So I'm going to write down the answers. If you want to work on them on your own time, fine. Whatever I don't cover in class, you won't have to worry about for the exam. I just thought that, I don't know, you might find this interesting. Some students really enjoy applications. And then second page, same thing. We're not going to have time for that next time. So if you are interested, number 15, the answer is, let's see if I can find it. System 1, 88.5, and System 2, 87.5. It's just matrix multiplication that you're doing here. And then for here, you're going to get 632 and 1433. You can just check if you want to. It's up to you. I'm going to put up some homework, though, for you to work on just a couple more of those. Well, actually, I don't know if I'm going to even assign anything from 6.1. Maybe some applications out of 6.1. And then out of 6.2, maybe a system that had fewer equations than variables. And then I'll assign you some 6.3 matrix operations. On Wednesday, we're going to be working on 6.4. You're going to be doing a lot more row operations again in 6.4. So prepare yourselves and make sure that you are ready to go, because you need to not be confused about row operations by the time Wednesday comes around. Your test is a week from today, and then a week from Wednesday, it'll be Thanksgiving break. And by the time you come back, it'll probably be almost December. Might even be December 23rd. Oh, it'll be November 30th. Oh, guys, we're wrapping up here fast. Have a wonderful evening. If you want to stick around for the office hour, I'll be on for another 15 minutes. Bye-bye.